This video covers the notes for the first section of chapter 3, so notes 3.1. Here we're going to be discussing scatterplots and related correlation. Scatterplot is a type of graph which uses an XY coordinate plane, or in an XY coordinate plane. So we're going to have data. The data is going to have, each data point is going to have two values. It will have an X and a Y value. Okay, so this is referred to as bivariate data. And this data is also quantitative, so numerical data. But each, say, person or individual data value, data point, will actually be associated with two pieces of data. One numerical value for each of two variables. All right, so a scatterplot graph is a graph that shows the relationship between these two variables. Often, most of the time, we're going to have some sort of explanatory variable. That variable will be the sort of the input, or the variable that explains the response that we see in the other variable. So as we increase the explanatory variable, we're going to see what happens to the response variable. So the explanatory or input or x-axis, it's going to be always plotted on the horizontal axis. The response variable, the maybe independent, a dependent variable that we, if you want to relate it to algebra, an algebra course. So the response variable will be the variable plotted on the vertical axis. This is the y variable, the output variable, the dependent variable. Here we refer to it as the response variable. All right, here we have some data. It is the mean math score by state. So there's 50 data points here. Each point represents one of the states here in the United States. And so each point has represents two different variables. The x-axis is the percent of that state, the percent of graduating high school students who sat for the SAT that year. And then the vertical axis, or the explanatory variable, will be the mean SAT math score for the entire state. So let's just look at one point. For example, this point here. It appears that that represents a state. Again, we don't know what state it is, but a state where about 18% of the students took the SAT. And I don't know, I'm going to estimate something like the average score for the math on the SAT was a 500. Okay. So we want to see, is there some kind of relationship? Well, this relationship, you notice, like all these points up here, those are really high mean scores. But if you look at it as far as what percent, probably less than 10% in those states, 10% of the students took the SAT. So you would expect if fewer people took it, the mean score would be higher. It kind of makes sense. Not everybody's taking it, just the people who are really prepared for college, who are going to plan to go to college, they take it and they score higher. Whereas, say, up in this region, a very high percentage, over 90% of the people took the SAT, but the average score was something like a 470, which is low. So there appears to be a negative relationship here. As a percentage of students take it go up, the average or mean SAT math score goes down. All right, so what we want to do is we want to look for an overall pattern and then be on the lookout for departures from that pattern as well. If we are asked to describe the pattern that we see in a scatterplot, or between the two variables, you must always talk about three things. The direction. So in that last graph, we had a negative relationship. As as the explanatory variable increased, the response variable decreased. So that would be a negative relationship. Is it linear? Is it clustered? Is it curved? The form. Now this chapter is really talking about linear relationships only. So most of the things we deal with in this chapter are going to be relationships that are linear. Now they may not be very strongly linear, but all the calculations we do are based on linearity. So even though there are other forms other than linear, just know that if it's not linear, we can't really work with it in this chapter. Okay. So if you want to talk about the direction, positive or negative, the form, linear, weakly, not very strong linear relationship maybe, but linear is kind of generally what we're going to say. And then the strength, is it a strong relationship or is it weak? How closely do the points fall on a nice line or a nice curve, that kind of thing. So if the points are kind of nicely patterned, then we're going to say strong. If they're more of a cluster, then we'll tend to say that they're fairly weak. We're also going to look for outliers. Now, outliers in this case have nothing to do with a 1.5 IQR like we saw in chapter 1. Outliers here are just points that tend to fall outside the rest of the pattern. So if all the data falls in sort of a linear relationship, except one point is way outside the line, then that will be sort of an outlier. All right, so if we look at this data, for example, this one might sort of be considered an outlier. What we really want to think about is like, what is the best fit line? So like, I'm just going to sketch it in. I mean, we're going to have ways of actually calculating it in a minute, but like, let's say that's the best fit line that goes through there. This point here is maybe an outlier. Certainly if there was a point down here somewhere, it would be an outlier. A point up here would be an outlier. It's outside the pattern of the rest of the data. All right, so one of our tools that we're going to use to talk about these linear relationships is correlation. And we use the lowercase r to denote correlation. And so that R value is going to be used to measure the strength, again, only for linear relationships. So if the data is got a clear curve to it, then it makes no sense to talk about what the correlation is. So just be careful, this correlation only relates to the strength of a linear relationship. And the value will deviate between -1 and +1. When R is close to either -1 or +1, the relationship is very strong. So the correlation is very strong. It's said to be strong. If it's closer to 0, then we'll say it's a fairly weak relationship, or the correlation is very low. Low magnitude-wise. You have to be careful because in mathematics, -1 is lower than 0. So when we say a very weak correlation, we mean a correlation close to 0, where the magnitude of R is close to 0. All right, so let's practice making a scatter plot here. So we have, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 teams in a college football conference. And what we have recorded is the average points per game over the season, and then also the number of wins that that team had that season. All right, so let's think about the variables. Which one would be the explanatory and which one would be the response? Do we expect one to influence the other, or we could use one to predict the other? So I think if you think about it, the points per game, the higher that is, we would kind of expect the more games you're going to win. So the points per game would be the explanatory here, I think, and the number of wins as a result would be the response. Okay, so what you want to do is label and scale your axes, and then plot your data values in the graph that you have. So I have here just some graph paper, and so we want to figure out like what scale to use so that we can fit our data. Now, what you don't want to do is start necessarily at 0 and go to 100. Sure, I think all of our data would fit if we're using points per game on the horizontal axis. That data would all fit. But what we want is we don't want to go from 0 to 100 because then all of our data will be scrunched down in one little area. We want our data to be spread out as best we can across the whole thing, but making the graphing of plots easy too. So in other words, don't make the scale so that the distance between tick marks is like 0.75 points. I mean, that's just crazy. So let's just kind of keep it simple. Look at the lowest value. It looks to be like 15. The largest value seems to be something like 36. So, you know, let's do 15, and then there's 5 tick marks. So let's go by 5. So we have 15, 20, 25, 30, 35, and 40. You don't have to start the very first X value on this line. So we don't have to make that 15.8. All right, it would just make things so horrible to try to graph. So let's keep it simple when we're doing these by hand. So 15 and 20, 25, 30, 35, and 40, I think works. All right, so now let's think about the vertical axis or the y-axis. Lowest value is 2. Highest value seems to be 13. In that case, maybe starting at 0 to 14. Like 0, 2, 4, 6, 8, 10, 12, 14 probably makes sense. All right, and so once you do that, then plot all your points. Pause this video if you want and finish that, and then start it up again. All right, so this is kind of what it should look like. Does there appear to be a relationship, or describe the association or relationship between the two variables? All right, so this means we're using our 3 things, right? The direction, the form, and the strength. So in one sentence, we could say that the relationship between points per game, average points per game, and number of wins appears to be a fairly strong, positive, linear relationship. So say those 3 things, right? The direction, the strength, and the form, in any order. It doesn't really matter the order, just so that it sounds right. Okay? Oh, also, don't forget to label your axes. So make sure that you've got your well, technically you should have titled it as well. So title it, and then your X and Y axis should be labeled. All right, so this slide is simply having you practice a little bit. Now, we're never going to actually expect that you look at a graph and know exactly what the R value is, right? Oh, that one is 0.8, or that one is 0.7. No. But in this case, I want you to try to take a stab at these. So guess what these 6 are. Put down on your paper what all 6 are. Pause the video, take a minute to do that, and then start it back up again, and we'll discuss. All right, so let's look at this first one. Clearly it's positive, right? It's got a positive relationship as X goes up, Y goes up. Now there's no scales on these or anything like that. We're just kind of looking at it holistically sort of here. So definitely positive, and actually that one is pretty strong. It's 0.9. So that is a fairly strong linear relationship. All right, the next one. So if that one's 0.9, this one ought to be a little weaker. That one ends up being positive, but 0.7. All right, and then the third one, it's not perfectly on a line, so I wouldn't call it -1, but it's pretty close. So it's a -0.99 actually. Okay. All right, the next one. Think about drawing a best fit line. Like, where would that best fit line go? It's kind of horizontal. Like, the best fit line would probably be somewhere here, fairly horizontal, and so as a result, that one is 0. As X increases, Y isn't increasing, so they can't really use the X value to predict the Y value. So this always happens. You get R equals 0 when the when the best fit line, we'll talk about that in the next section, but when that best fit line is horizontal, it's going to be an R value of 0, or the next one. So it kind of appears to be negative, but not super strong. That one is 0.5, which is kind of considered moderately strong, kind of in the middle of the road. Sort of not very strong, but negative for sure. And then the last one, it actually has more points, but really it's not any stronger than the last one. So it's still moderately strong or moderately weak. It's kind of in the middle, however you want to say it. So again, we're not going to ever give you a graph and expect that you can pick this out. If we gave you something like this and it was multiple choice, then we wouldn't give you, like if we gave you this first graph, we wouldn't, if it's multiple choice, I wouldn't give you 0.85, 0.9, 0.95. I wouldn't expect you to be able to differentiate, but you should be able to say, oh, this one's fairly strong, this one's a little weaker, this one's pretty weak, right? So you should be able to look at it and say the strength of it, without R value, if you have it, will help you determine that, how strong it is, but you should be able to kind of look at it by process of elimination. In a multiple choice, you should be able to figure it out, because we would make it obvious, right? Some of them would be negative. Oh, clearly this is positive, right? It's not 0, it's not 0.5, it's much stronger than that, but again, we wouldn't give you like 0.85 and 0.9 and expect that you would know the difference. All right, so we're not really generally going to calculate the R value by hand, but we are going to do it once to help us just visualize how it's done and why it is kind of what it is, like how it comes out to be negative versus positive in the calculation. So we're going to do it once with some real simple data, and just kind of follow along. Pause this video whenever you're trying to do calculations, but ultimately it just kind of wants you to be experienced at how we did it, but we'll never do this by hand again. All right, so we have some data. We asked 15 freshman boys that we surveyed, what is, how many minutes on average do you game, Xbox, whatever, per day, and then what is your GPA? All right, so we would kind of expect this to be a negative relationship if you think about it, right? The more you're gaming, the less your GPA is probably going to be, right? The more time you spend gaming, the less time you're going to spend studying, and so your GPA will probably be lower the longer you're gaming every day. All right, so we want to first calculate the mean and standard deviation for both the explanatory and response. So we already talked about it. It kind of makes sense that your average time per day is going to affect or predict your GPA. So the time spent gaming will be your X, or your explanatory variable. Your GPA, as a result, will be your response, or Y variable. All right, so the first thing we want to do is show you how to calculate the mean and standard deviations for both sets of data. All right, what you should do here is plot your 5 data values. Pause the video and then restart it once you're finished. All right. So we've plotted those, and now what we want to do is calculate our mean and our standard deviation. So we're going to use our calculators for this, because we're going to need this data placed into our calculators later, so we might as well do it now and help us to calculate the mean rather than doing it by hand. So you want to take a minute, pause the video, put the X data, which is the time, into list 1, and the Y data, which is the GPA, in list 2. So hit Stat and then choose Edit, and it will take you to your lists. So put in list 1 the X values and list 2 the Y values. When you're finished, unpause the video. All right, now what we want to do is go back and hit Stat. This time cursor over to Calculate, and it gives us, we want to choose a 2 variable stat, two var stat. Now we've done this in chapter 1 when we did a 1 var stat, because we were only dealing with 1 variable, but we've got 2 variables, so we'll choose two var stats here. And then it gives us this. And so what we want to do is we want to say our X list is in list 1 and our Y list is in list 2. Let me just say one cautionary thing too, is make sure these data values line up. You know, these cannot just be in any order. Like, okay, it's okay for what we're doing now, but in a minute when we need this data, it's going to be pretty important. So make sure that 65 is right next to the 2.3. That the 34 is next to the 2.6, and so on, okay? Again, it won't matter for this calculation, but it will matter in later ones. So if you like accidentally forgot to put in 2.9, you can't just put it in at the end, all right? That'll give us an error. The calculation won't work out right when we go to later things. All right, so we go, we do stat, we go to calculate, we put the X list is list 1, the Y list is list 2. Remember, if those aren't already in there, then do second 1 and second 2 to get L1 and L2. Hit calculate, and you get something that looks like this. So the very first thing is the X bar. Look here, the S sub X. We don't want the sigma, but we want the S. That's the standard deviation. So our X bar, or our mean, is 38. And the standard deviation is 19.0. Cursor down, this little arrow here means there's more stuff to display that can't display, so cursor down and you'll be able to see the Y bar and the S sub Y, all right? And those values, just put them in your table. The mean 38 for the time, the mean for the GPA is 3, standard deviation 19, and 0.6. Okay, so we have our data values plotted in our scatter plot. Take a second and just, for the heck of it, predict what you think your R value will be. I think everyone can look at this and say, well, it's definitely going to be negative, but take a stab at it. Let's see how you do. We're going to calculate it by hand, and then we're also going to show how you do it with your calculator. So, but let's just try to predict it on our own first. So write it down right next to the graph somewhere, what you think your R value is. All right, so let's draw in our bars. So that means our X bar and our Y bar. So the mean of the X values and the mean of the Y values. So our X bar is 38. So we'll draw in a vertical line right there at 38, where our X bar is, and the same thing, horizontal line where our Y bar is at 3. Notice this X and Y bars kind of create 4 quadrants here. And furthermore, if we look at these 2 points up here, they are below the X bar, but above the Y bar. These 2 points are the reverse. They are above the X bar, but below the Y bar. That will come into play in a minute. All right, so the actual calculation. Back in chapter 2, we learned about z-scores. And so we here look and we calculate the z-score for each X value and the z-score for each Y value. So we look at this 27, and we subtract the mean, right, of 38, and we divide it by the result by 19, the standard deviation. So it's the z-score for the X data value compared to all the other X values, okay, the distribution of X values. And then we do the same thing for the Y, the z-score for 34. 34, where is it in the distribution of other Y values? So that's what a z-score does. It tells us where it is. So notice that our z-score for the X is negative because it is below the X bar. This point's Y value, 3.4, is above the Y bar, so it is positive. So the resulting product, when we multiply across and get the product of the z's, that is going to be negative. All right, and so if we look at these values, notice most of these are negative, right? So we had a negative z and a positive y. This point was above the y bar, but below the z bar, so it's negative. The product will also be negative. the whole key is that most of our points are in these quadrants. And so as a result, most of the products of the z's are negative. Only one point is in these quadrants, this point here. And so if we add up all of our products of z's, notice the sum of all those products is going to be fairly negative, and that's what makes our z-score negative. All right, so we take that sum of all the products of the z's, and we simply take that and divide it, but not by 5 data points, but one less than that. Just like we saw when we were doing standard deviation calculations for samples, we divide it by one less. It has to do with the degrees of freedom beyond the scope of this class, but we're dividing by 4, and so our R value, or our correlation, is negative. We knew that was going to be negative, but it's fairly high, negative 0.88. All right, now let's look at how we would do this on our calculators. All right, so we have our data already listed in list 1 and list 2. The time gaming data is in list 1, and the corresponding GPAs are in list 2. So remember too that these have to correspond. Each row is the X and Y value for a particular freshman. You can't mix those up, things won't work. All right, so you want to hit stat and then calculate, and then your options are listed here. You have to scroll down a little bit. Got to be careful. We want to use linear regression, but we don't want number 4, AX plus B. This one is what we would do if we were doing linear regression in an algebra class. Statistics and algebra branches of mathematics diverged at some point, and so in algebra, B universally means, in a linear regression, the y-intercept. However, in statistics, B, the same symbol, B does not mean the y-intercept. It's universally known in statistics as the slope of the line. So you must use linear regression 8. Otherwise, you're going to say B is some value, and it's not. It's the wrong thing. Okay, so A for us is the y-intercept. B is the slope here. All right, so select that, and you get something that looks like this. It's asking where's your X data, where's your Y data, and then hit calculate, and you get this. Now, a good portion of you would not have this displayed on your screen. The R squared and the R value just don't show up. And so what you really have on your screen is something that looks like this. All right, so for some reason, your TI-84s generally, by default, come from the factory with a certain thing turned off, and this is one thing that it affects it. So we have to go change a setting in your calculator, and I'm going to show you how to do that now. Okay, so first thing you want to do is you want to hit the second button, the blue second button, top left corner of the buttons on your calculator, and then hit 0. So the second function of the 0 button is catalog, and so this is a list of all of the commands that are built into your calculator. So you could do computer programming in your calculator. It's got all kinds of commands built in. What we want to do is get down to something called diagnostic, and it starts with a D. And so you could use your cursor button and cursor down all the way to the D's, but that's kind of annoying. So instead, notice that there's an A displayed in the top right corner that indicates that you're in alpha mode. So if you hit any button on your calculator, it's going to refer to the letter on the right top of each of the buttons. So what we want to do is we want to hit the D button, which is the alpha function of your inverse, or X to the -1 button. So look at your X to the -1 button. It says matrix above it, and next to it says a D. So just hit that button, and notice it instantly takes us down to the D's, and then just scroll down. Use your scroll button to scroll down to something called diagnostic on. Once you do that, hit enter to select that, and then it pastes the command back on your home screen, at which case you can hit it again, enter again, and it executes the command. Nothing really seems to happen, just says like done, right? And so then what you want to do is you want to go back and rerun your linear regression. So hit stat, calculate, and then hit the 8 button. It does linear regression. So 8, linear regression, again, list 1, list 2 is your X and Y list, and then calculate. And now you've got your R squared, which we'll talk about in the next section, and we have our R. So notice, we had hand calculated it to be 0.88, which is correct if we round to 2 decimal places. So negative 0.88, or about, if you wanted to say, about negative 0.9. All right, so let's kind of review this. This graphic sort of shows us a scale of the correlation and its possible values and how strong and weak or weak they are. So anything between 8 and 1, 0.8 and 1 is considered strong. Anything around 0.6, 0.7 considered moderate. Anything below 0.5 would probably be considered weak. And then the same thing on the negative side as well. Remember, things correlation values close to 0 means that there's really almost no correlation. All right, some things to know about correlation. If I were to reverse the explanatory and response variables, so some situations there's no clear explanatory variable. Like for example, I could use my arm span to predict my height, or I could use my height to predict my arm span, right? So it doesn't really matter if I flip-flop the explanatory and response variables in the calculations, the correlation will not change. The predicted model might, right? Definitely it might. The slope of the prediction line that would change. We'll talk all about these things more in the next unit, but the correlation does not change. All right, the changing units. So if I had miles per gallon versus kilometers per liter, that doesn't matter. So the R value is actually dimensionless. It's all z-scores, which don't have units, and so R values will not have any units. So changing the units in the data from feet to meters or whatever does not affect the R value. It has no units. We already said that. It's just a number, no units. Correlation. If you have a high correlation, it does not mean that the explanatory variable is causing an effect or a change in the response variable. So causation can only be shown, and we'll see this in the next chapter when we start talking about experiments. You have to have a randomized controlled experiment to indicate causation. All right, again, this is only quantitative variables, no categorical variables. You can't say like eye color. It cannot have a correlation relating categorical variables. The correlation measures the strength of purely linear relationship. So if the relationship is clearly curved because you plotted the data and there's a strong curve to it, then correlation makes no sense. So don't even bother calculating a linear correlation for nonlinear data. R values close to 1 and negative 1 do not necessarily guarantee a relationship that's linear. So if you just blindly calculate the R value without plotting the data, you might say, oh, I get an R value of 0.9, therefore it's a very strong linear relationship. Whereas when you go plot the data, it's curved. And so the correlation makes no sense then in that case. They're strongly affected by outliers. If we saw earlier, we talked about what an outlier is. It's outside the pattern of the rest of the data. Putting in one of those points will generally strongly weaken the correlation or the R value. And then not, an R value just by itself is not a complete summary. We want to look at X bars. We want to look at the means and the standard deviations as well. Those will help us find other stuff as well in later sections of this chapter. All right, so you do not have these in these next couple of slides in your notes. It's not something we do a whole lot of in this class, but just want to make sure. Sometimes the scatter plot has the X values have a clear chronological order to them, or something we call a time series plot. So we could look at life expectancy in the United States based on the decade. So 1940, 1950, 1960. So it's a clear order to the data. The explanatory variable is the year. The response variable is the life expectancy, average life expectancy. So if we plot this data, you can see it looks something like this. Only when it's a time series plot where these data points are in order, then that's the only time really we would connect the dots. So generally with a scatter plot, do not connect the dots because there isn't a, here it's time series, there's a logical progression through these data points. If we look back at the verse example we did today, the percent of high school students taking SATs, if we took that data and we plot it and we connected the dots, it would make no sense. So this is what you would get. So only connect the dots when we have a time series, and we don't deal with it a whole lot this year, but sometimes you'll see that. All right, this is the homework. It is due next class. Also, you might, if you hadn't read this section 3.1, do that. And you should also begin reading section 3.2. We'll spend a couple of days going through the next section. It's kind of involved, but you can begin reading through section 3.2 for next class as well.